This video is all about how to make magma. As you'll discover, magma isn't very common inside the Earth, and it takes special conditions to make it. Those conditions only exist at special kinds of plate tectonic settings, specifically at divergent plate boundaries, at subduction zones, and at hot spots. You can also make magma when rock comes in contact with other magma, but we'll leave this case until the end. Melting mostly takes place in the mantle, which is made up of the rock peridotite. Here we have some xenoliths of peridotite, which are contained within a basalt, which has been brought up to the surface by volcanism. Peridotite typically contains 3 to 4 minerals, as is shown here. We have the green, green mineral here is olivine. The darker green mineral is one of 2 types of pyroxene, and there's usually some other aluminous phase, either plagioclase or a spinel or a garnet phase as well. In these animations, I'll represent the minerals in peridotite with the various colored shapes as that are shown in this little cartoon here. So let's start out with the peridotite and imagine what happens when we start to heat it up. Well, nothing is going to happen until we reach a temperature of about a little more than 1,000 degrees C. At this temperature, a tiny amount of the rock melts. That's the stuff shown here in red. The temperature at which the rock begins to melt is called the solidus temperature. If we keep increasing the temperature further, more and more of the rock will melt until we eventually reach a temperature at which the rock is entirely melted, say at 1210 degrees C. The temperature above which the rock is entirely melted is called the liquidus. Notice that the melting interval between the solidus and the liquidus isn't small. It's typically on the order of several hundred degrees C. This means that within this temperature range, both solid and liquid are stable. To make magma, all we need to do is cross the solidus. We have to raise the temperature of the rock or somehow put the rock at a temperature which is above its solidus. We don't have to actually reach the liquidus. Once a few percent of the rock melts, the liquid gets squeezed out and rises to the surface because of buoyancy. So we don't actually have to heat the rock much higher than its solidus temperature in order to generate magma. To understand what happens to make peridotite melt, we use a phase diagram. This is simply a graph of temperature on the x-axis versus pressure shown here on the y-axis. And what we have shown here is the stability field of a peridotite under various combinations of temperature and pressure. Either we could have all solid present, no liquid at all. We could have all liquid present, no solid at all. Or between the liquidus and the solidus, we have a mixture of both solid and liquid present. Notice that because we want to make this diagram sort of look like a slice of the earth, we usually graph it so that the pressure increases downwards, and so that increases in pressure going downward correspond to increases in depth going downward. I've also shown the depth on the right hand side of this diagram as well. Here, for example, is how we'd actually use that phase diagram. So let's say we want to know what the state of the mantle, which is made of peridotite rock, is at 1200 degrees C and 65 kilometers depth. Well, if we're at 1200 degrees C, we have to lie along this vertical red line. And if we're at 65 kilometers depth, I'm going to use the right hand scale here to look at the depth here. So we have to be along this vertical line here. We have to be at 65 kilometers depth, corresponds to this blue line here. So if we're at 1200 degrees C and 65 kilometers depth, then we have to lie at the position given by the yellow dot, which is of course within the field of all solid. So in other words, if we were under those conditions of temperature and depth or corresponding pressure, we would expect to see all solid. We wouldn't expect to see any liquid whatsoever. The geotherm, which is shown here in green, represents the combinations of temperature and pressure that are typically found within the Earth. Notice that as we go down, as we go to higher pressures or higher depths, the temperature increases. But also notice that although it increases, the temperature never reaches or exceeds the solidus temperature, which is shown as the blue line. So in other words, at all of the temperatures and pressures corresponding to the points along the green line, which represent the typical conditions inside the Earth, the peridotite rock in the mantle will lie within the field of all solid. In other words, there isn't any liquid present at all. The mantle in general isn't melted. And this suggests that in order to make magma, then it takes some kind of special condition, something that's a departure from this normal condition, in order to create the conditions under which a rock finds itself at a temperature above its solidus and thus can begin to melt.